Hello friends, in this video I am going to discuss Clausius inequality, entropy principle, temperature entropy plot and its relationship with heat interactions. So to discuss Clausius inequality, let us consider a cycle ABCD in which process AB, a general cycle, whether it is either reversible or irreversible, whereas all other processes are reversible processes. Let us divide this cycle into small elementary cycles by drawing reversible adiabatics and reversible isotherms like this. Now let us consider one of the elemental cycles in which delta Q amount of heat is supplied at temperature T and delta Q2 amount of heat is rejected at temperature T2. Now for this efficiency of any cycle is given by 1 minus delta Q2 divided by delta Q. Efficiency of general cycle or any cycle is always less than or equal to efficiency of a reversible cycle. So that can be obtained in this way, that is 1 minus delta Q2 divided by delta Q is less than or equal to 1 minus delta Q2 divided by delta Q of a reversible cycle. By removing 1 and minus symbol on both left and right hand side, that can be reduced to like this, that is delta Q2 divided by delta Q is greater than or equal to delta Q2 divided by delta Q reversible. That greater than symbol has come in this way, that is it is illustrated like this. I have taken like this 1 minus 0.7 is less than 1 minus 0.6. The term this 0.7 indicates this ratio delta Q2 divided by delta Q of any cycle, whereas this 0.6 indicates delta Q2 divided by delta Q of a reversible cycle. Here 1 minus 0.7 is 0.3, which is actually less than 1 minus 0.6 which is 0.4. So this is true. But when it comes to like this, that is if 1 and minus symbol are removed on both the sides, we will have like this, that is 0.7 and we will have 0.6. Obviously 0.7 is greater than 0.6. In that way this term has been obtained. So in the next step, when both the numerator and denominator of left hand side and right hand side are swapped or exchanged, once again we will have less than or equal to symbol. So we have delta Q divided by delta Q2 is less than or equal to delta Q divided by delta Q2 of reversible cycle. Now for Carnot cycle, we have delta Q divided by delta Q2 reversible is equal to T by T2. So the previous equation for this term delta Q divided by delta Q2, if you substitute T by T2 as this T by T2 is equal to delta Q divided by delta Q2 of a reversible cycle, then we will have the equation like this, that is delta Q divided by delta Q2 is less than or equal to T by T2. Now by exchanging or rearranging this delta Q2 and T on left hand side and right hand side, we will get the expression like this, that is delta Q divided by T is less than or equal to delta Q2 divided by T2 for any process AB, whether it is reversible or irreversible. For a reversible process, differential entropy change ds is equal to delta Q reversible divided by T, that is equal to delta Q2 divided by T2. So this is for a reversible process. For any process AB, this delta Q divided by T is less than or equal to ds. Now we will have for any cycle, that means cyclic integral of delta Q divided by T is less than or equal to cyclic integral of ds. Since entropy is property and cyclic integral of any property is 0, cyclic integral of delta Q divided by T is less than or equal to 0. This equation is known as the inequality of Clausius, and this provides the criterion for reversibility of a cycle. Now let us see the criterion. If cyclic integral of delta Q divided by T is equal to 0, the cycle is reversible. If cyclic integral of delta Q divided by T is less than 0, then the cycle is irreversible and which is possible. If cyclic integral of delta Q divided by T is greater than 0, the cycle is impossible since it violates the second law of thermodynamics. So that is about Clausius inequality. Now let us discuss entropy principle. So for that, let's have for any infinitesimal process undergone by a system, we have ds is greater than or equal to delta Q divided by T. For an isolated system which does not undergo any energy interaction with the surroundings, in that case dq is equal to 0. Therefore, for an isolated system, ds isolated is greater than or equal to 0. In this term, if this delta Q term becomes 0, so this ds isolated is greater than or equal to 0. For a reversible process, ds isolated is equal to 0 for reversible process. Now that means S equal to constant, that is entropy equal to constant. For an irreversible process, ds of isolated system is greater than 0. This proves that entropy of an isolated system can never decrease. It always increases and remains constant when the process is reversible. So this is known as entropy principle. That is about entropy principle. Now let us discuss temperature entropy plot and its relationship with heat interaction. The infinitesimal change in entropy ds due to reversible heat transfer delta Q at temperature T is given by ds equal to delta Q reversible divided by T. So for a reversible process that undergoes infinitesimal change in the state of a system, there will be infinitesimal change in entropy, and that is caused by reversible heat transfer delta Q. So that is ds equal to delta Q reversible divided by T. If delta Q reversible is equal to 0, the process is reversible and adiabatic. As it is already known, in case of adiabatic process, the heat interaction is 0. So when there is a reversible process and heat interaction is 0, that case this change in entropy is 0. That means entropy is constant. That is called as isentropic process. A reversible adiabatic process is therefore an isentropic process. Now delta Q reversible is equal to T into ds. When this equation is rearranged, we get this equation, that is when this T is brought to left hand side, then delta Q reversible is equal to T into ds, or this equation can also be written as Q reversible is equal to integration from I to f T into ds. Here if we take for example if we plot change of state from initial equilibrium state I to final equilibrium state F on TS diagram, and when it follows the path, reversible path R, the area under this curve indicates the amount of heat transferred during that process, so that Q reversible is equal to integration from I to F T into ds. Now, when there is an isothermal process where temperature is constant, if there is a state of change from initial equilibrium point I to final equilibrium point F, the area under the curve indicates the total heat transfer during that process. In that case, Q reversible is given by integration from I to F T into ds, that is equal to T into SF minus SI. Here SF is entropy at final state and SI is entropy at initial state point. So that is about temperature entropy plot and its relationship with heat interaction. And that's all in this video. Thank you.